So, hello and welcome to lecture number 15 on convex analysis. So we're officially in the second half of the lecture. So I once again put in a question in the chat. Oh, but read the chat. You notice that there are a bunch of new people here in the chat, and this is because of the following. Starting from next week, this course will be a joint course for this usual convex analysis course here at TU Braunschweig, but also a convex optimization short course for two mathematical centers, one in Senegal and one in Rwanda, part of these African Institute of Mathematical Sciences. So we will have a bunch of new students here attending this lecture for the next 3 weeks. So not starting today, but starting next Tuesday. But so since they are the students in Rwanda and Senegal at IMS brushing up on their basics of convex analysis, so that they can follow the stuff on convex optimization in the next 3 weeks. They already joined the chat right now and maybe checking the lecture notes and stuff like that. So, but from next week on, we will have a few more people attending here, hopefully. And there's another announcement from next week on. This live lecture on Tuesdays will not be at 9:45 anymore on Tuesdays, but on 11:30. But I will write an official announcement on StudIP on that. Otherwise, but I also noticed that there were not that many live listeners here, so probably many of you won't notice that much. Anyway, okay, there's the question. No answers up to now. The question is, if a function is the indicator of a convex and closed set, then its conjugate is also an indicator function. Is it true or false? Okay, and maybe I wait if there's a few answers coming in, and if not, we just leave it like that and talk about that later. Okay, apart from that, let's start with our lecture today, which is Fenchel-Rockafellar Duality. So lecture number 15, Fenchel-Rockafellar. Yeah, these are one of the two of the very big names in convex analysis. Fenchel-Rockafellar. Rockafellar still working at the University of Washington and still publishing papers, and Fenchel, I don't know, did his great works in the 50s and 60s. Okay, so we know the Fenchel inequality, the Fenchel equality. That's an important thing, and we're going to use that a lot. The Fenchel equality states that a vector p is a subgradient of f at some point x, if and only if it holds that f of x plus f star of p equals to the scalar product of x and p. So we can characterize the containment in the subgradient by an equality involving the conjugate. One could even think that this the desire to characterize this by an equality is kind of the motivation for defining the conjugate in the first place. But because this statement here is symmetric, in x and p, and we know that the conjugate of a convex lower semi-continuous proper function is the function itself, we can also write that this is equivalent to x being in the subgradient of f star of p. Okay, so this is just the Fenchel's equality revisited. And so from this we can deduce if x star is a minimizer of f, so this is by Fermat's principle equivalent to saying that 0 is in the subgradient of f at x star, Fermat principle. But then now subgradient inversion, we can put the subgradient to the other side and need to conjugate this. So this is the same as saying that x star is in the subgradient of f star at 0. So this says that if we know the conjugate exactly, you just have to evaluate the subgradient at one point to solve an optimization problem. So the dual function, or the conjugate function, contains a lot of information about the function. Contains the same information as f, of course, because it's kind of in a one-to-one correspondence, but it contains as much into the information in a way that you just evaluate the subgradient at a certain point to solve a minimization problem. So certain things are much easier in the conjugate than in the primal. So minimizing a function can be tricky, but evaluating the subgradient can be simpler. But the catch is that often, of course, conjugating the function is basically at least as hard as solving the minimization problem, as we see in the equivalence here. But we'll see that we can make use of this fact that the dual function can really tell us something about minimizers in the following. Okay, and so in this section we're going to treat a special case of optimization problems, and this is the case looks like as follows. The minimization problems are of the form we minimize over x in Rn, and the function, the objective looks like f of x plus g of ax. For f is a convex function on Rn, g is a convex function on Rm, and A is the matrix of the appropriate dimension, m times n. Okay, and I forgot to say that f and g are proper convex and lower semi-continuous. Okay, so in other text books or other lectures you will see the same thing when x comes from, for example, a Hilbert space. Then one would need to adapt here a little bit, saying that it's weakly lower semi-continuous. But also one could think about then A, of course, is a linear map from one Hilbert space to another. And then there are different notions of continuity which could be of importance here. Could be a bounded operator, could be even a compact operator, for example. And then you will also see the situation where X comes from a Banach space, and A maps between two Banach spaces. So these are two Banach spaces then, and then things get a little bit more complicated again because of different notions of continuity here and of boundedness, and no, boundedness is just one notion, but of continuity of the linear operator here. In this lecture we don't have to think about that. This is just a matrix and linear map, and because it's between finite dimensional spaces, this is always a continuous one. Yeah, so in Banach spaces you may think about different conditions like boundedness or closeness, for example, which is a different thing. Okay, so examples of this are, for example, the regularized least squares problem. So one example would be taking f of x to be alpha times r of x for some convex lower semi-continuous regularizer r, and g of y could be, for example, this function here, the least squares function with respect to some b, and then of course a is the same as a, and then this would lead to the problem minimize 1 over 2 ax minus b, so the least squares objective plus a regularizer. Okay. Of course, you could also do different things. You could also say, well, f could be the non-negative orthant, and then you would get least squares problems constrained to non-negative solutions, so non-negative least squares. You could also put an indicator function of any convex set here, and then you would have a convexly constrained minimum or least squares problem, and so on and so forth. There are just a ton of possibilities, so lots of problems can be phrased like this. Okay. So of course, what's the significance of this? And the significance of this lies in the fact that many problems that you formulate like this have then the problem that this A is an operator which at least you can always apply simply. So in the least squares problem, this would be multiplying by the matrix A, which often comes from data, for example, or is modeled by yourself. So this is something which you have under your control. And then F and G may be of the case that is, for example, simple to conjugate, simple to differentiate, simple to do the prox for, something like that. And in this case, the G is as good as it gets. So it's norm squared. Translated, so the conjugate is obviously also a norm squared tilted. It's differentiable. The conjugate is also differentiable. So this G is very nice, but the G after A may not be so nice. The conjugating may be difficult if A is not orthonormal and stuff like that. And in this example here, R is also under your control, so you may choose R in a way that you can differentiate or at least do prox operations or evaluate subgradients and stuff like that. And all these things may be simple for these individuals, for F and G and A, but for the joint objective, doing the conjugate is as hard as solving the minimization problem, so it may be very difficult. Okay, so how comes duality into play? Let's first do some non-rigorous manipulation to see how this works in general, and then we want to make this rigorous. So let's start again from our minimization problem. Minimize x over plus g t of x. And so the problem is somewhat complicated because you have a sum of two terms, of two convex functions, and also you have this linear operator here involved. But the good thing is that you kind of decouple all these problems by using the definition of the conjugate. So what we do here is we replace g by the definition of the conjugate. So the conjugate is taking the supremum over all, let's say, y in Rm, and then to write down the primal, we use the Fenchel-Rockafellar theorem, that this is exactly the point where you're going to evaluate ax times y minus the conjugate of y. Okay, and then of course you can put the supremum also here, and you end up with the min over x sub over y problem. F of x plus ax times y minus g star of y. Okay, and now this is a problem which in which all these problems are decoupled. So there's one nonlinear term which contains f x, there's one nonlinear term which contains y, and there's one bilinear term which contains x and y. So, but there's not the situation that you have x in two complicated ways or y in two complicated ways. So everything is nicely decoupled into three different terms here. Okay, but does that help? We'll see it kind of yes in a second. So, but first, so up to here, everything is rigorous. We just didn't do anything complicated. So now let's assume that this supremum here is actually attained. So you can write a maximum here. And then let's also assume that we can swap minimum and maximum, which is definitely not always the case. In most cases, so in many cases it's not. We'll see simple examples where it's not fulfilled. So let's just pretend it works. So if we swap that then and replace the max by a sub, so maybe I should highlight the terms which are not obvious here. So let's replace this by a max over y, and also we changed the order, but then let's just keep it as it is over here. Ax times y minus g star of y. So and then you observe that this guy here kind of looks like the definition of the conjugate again. You have this term which is linear in x, and you have this, but for the conjugate something is a bit different. You need a supremum, not a minimum, and also you need a minus sign in front of f. So but this works out. You could just add a minus sign here and pull a minus sign out. So what do? We pull a minus sign out of this term here, and do one more step. We also replace this guy here with the transpose matrix by x times a transpose y. So and then let's keep the max over y, and we pull a minus sign out, which turns the minimum into a maximum over y. And then we have minus signs here, and here I put the minus sign in front of aty, and here we have the minus sign for f of x, and I have minus g star again. Okay, so here let's check what we've done. We pull the minus side out of this over which we take the minimum, which turns the minimum to a maximum. Maybe I should add further brackets here. Then I have two additional minus signs in front of each term. So we put you have a minus f of x here, and then I also have a minus inner product, and I put the minus in front of the a transpose y. And now this guy here is exactly the conjugate, right? This under the assumption that it's attained, the supremum. So but this is exactly the conjugate of f at what point? At that point here, so minus a transpose y. So we end up with the maximization problem, maximizing over y the function minus f conjugate at minus a transpose y minus g star of y. Note that there are three minus signs here, right? One in front of each conjugate and one inside of the one conjugate where the operator is inside. Okay, and of course, you could, but we don't do it in most places. You could pull out the minus sign again, and then we end up again with the minimization problem over f conjugate of minus a transpose y plus g star of y. And then you notice that these two problems are exactly of the same type, right? It's the sum of two convex lower semi-continuous functions. One is evaluated at the optimization variable, and one has an additional linear operator in front. So, and so now, what is also interesting is that this is a minimization problem over Rn, but this is a minimization problem over Rm. So a different space, maybe for example much smaller than the space over here. So for example, if you're in the situation that this m is much smaller than n, this problem over here may be much smaller than the problem over there, so less optimization variables. Other things may happen that these two functions f star and g star may have better or more favorable properties than f and g. So for example, it may be that these f and g are merely convex, but f star and g star are differentiable. We will see that this is possible, and we'll even can write down when this is the case. So now you have these two problems, but the question is still why should we care about this problem here? It is of course kind of related to that. For example, if you would be just interested in the optimal value, we could just solve this problem if this step works. If this is really an inequality here, that's not clear. But if it works, we could just solve this problem here and would get the optimal value back of this problem over there. Okay. But there's more. In lots of circumstances, a solution of this problem over here reveals some properties of a solution over there. Sometimes it even describes them exactly. Sometimes there's a one-to-one correspondence for each. Well, that's just a map. For each solution over here, you get one solution over there, or the other way around. So that these two problems exist may sometimes be very beneficial. And even this problem in the middle here, this min-max problem, is also sometimes very nice to work with. So let's fix notation. So in the context of what we do here, this duality, this is called the primal problem. And this problem here is the Fenchel-Rockafellar dual problem. And of course, Fenchel-Rockafellar are sometimes omitted. But there are other dualities, for example, linear programming duality, which is actually a special case of this. You want to see this in the next lecture. Okay, so this is the motivation why what duality is about. And now let's start and try to do it more rigorously. And to figure out the relation between these two problems, we start from middle ground and from this problem here. Problems of this type here. And now let's do not care so much if it's a min or an inf or a sub or a max. We'll come to that, it's important. But we start with problems like this. So problems which are where we have a function which is defined on the product of two different Euclidean spaces. Okay, and these problems are called saddle point problems. No, not like that. Saddle point problem. So you have, for a saddle point problem, you have some function L which is defined on the product of two Euclidean spaces, and you allow the value plus and minus, values plus and minus infinity, and the goal is find a pair x star and y star such that the x star is the minimizer of or is one minimizer of L when you fix the second variable to y star, and the y star is a maximizer, argmax, of L when you fix the first variable to x star. Okay, and so this is the saddle point problem. You have a function on the product space, on some product space, and you want to find a pair, one in the one space and one in the other space, such that if you fix the second variable to y star, x star is a minimizer of that, and if you fix the first variable to x star, y star is a maximizer of that, and a pair like this is called a saddle point. So the goal of a saddle point problem is to find a saddle point, which obviously makes sense. So alternatively, you could write the following: x star, y star is a saddle point of L if you have for all x and y that L of x star y is smaller or equal L of x and y, smaller or equal L of x and y star. So this also characterizes saddle points, and we're going to need this characterization in a second. Just check that this is actually the case. Okay, so let's analyze problems of this type. So first proposition, 15.1. Yeah, we always have the so-called min-max inequality, which is a funny name because it contains either a min or a max. But what is true is that the infimum over x after the supremum over y of some saddle function, this is sometimes what you call this saddle function, is larger or equal to the supremum over y after the infimum over x. So this is the min-max inequality. So first infimizing and then supermising gives you something smaller than first supermising and then infimizing. So kind of what you first do matters more. If you first minimize, then you get a lower thing in the end. Okay, that's one thing. And moreover, you can also say x and y star is a saddle point of L if and only if it holds that the min-max in this order, so y and x, is the same as the max-min over y and x in this order, and this is exactly the value of the saddle function at x star y star. Okay, so this is another way to describe a solution of saddle point problems. So with this arg-min arg-max formulation, with this chain of inequalities, or with this that you can calculate the min-max or max-min in either direction, either order. Okay, so the proof of this min-max inequality is it's very simple. It's ridiculously simple. So of course you have for all x bar and y bar, you always have that if you take L at these 2 points, that's of course less than what you get if you maximize over y. Right? So this is bigger than that, because this is a particular instant. And you also can go the other way. The infimum over x is of course less than L of x bar and y bar. Okay, and now you can take the infimum over x bar here and the supremum over y bar there, and you're done. So this gives inf over x bar supremum over y of L of x bar y is larger or equal to the supremum over y bar infimum over x L of x and y bar. And because these are now all local variables, you can just name them as you like. So I named this y bar, but you could just rename it to y, because this y is a local variable. So this is just the first claim. Here is proven. So now let x star y star be a saddle point. And we want to show that this holds here. Okay, and then we use the characterization with the star over here. We get that L of x star y star is equal to, and I do it like, oh no, not equal, it's larger than, equal to the max over y of L of x star y, and because it's a saddle point, this maximizer exists, so I can really say max over there. This is of course larger than what I get if I infimize over x after I maximized over y, of L of x and y. And now by the min-max inequality, if I swap these guys, I get smaller again. So it's smaller after swapping, and then I need to write supremum because existence is not guaranteed anymore. So this is the min-max inequality here. But here inside we have the minimization problem over just one variable fix, and we I forgot the argument for that, so we can replace this by a minimum here. So maybe not here, probably not, so probably it's just simpler to skip that, because we could of course make it smaller by omitting the supremum here and replacing y by y star. And then we have existence of minimizers by assumption that it's a saddle point, right? The saddle point assumption includes that the minimizer exists, but also by assumption this is exactly L of x star and y star. So we have a chain of inequalities, but left and right are equal. So we have equalities all over the place, and this also implies that we can replace this sub-inf by max and min. Okay, so this is the one direction, and conversely, let's assume that this 2-star thing over here holds. Then we have that the minimum over x of L of x and y star. This is from this is then smaller equal L of x star and y. Yeah, of course. And this is smaller equal than the maximum over y over L of x star and y. Oops. What do we have there? And then combining it with our then combining it with sorry. So let's assume we have that, and then you can add the min and the max on the both sides, and you see that you get the same thing, and you always get the same thing, which says that you have equality all over the place, and which shows optimality or solution of a saddle point problem. Okay, let's first make an example that, of course, you cannot always swap things here. A very simple example, probably the simplest example where you can swap min and max, even though they're all attained, is maybe the function L of x and y, two real variables, is sine of x plus y. If you do that, then the supremum of sine of x plus y over the full real axis, or bound intervals, or basically more or less any set, and after then taking the infimum over y, this evaluates to +1, right? If the supremum over the sine, no matter what value of y here is always +1. But if you do it the other way around, first taking the infimum over the sine of x plus y over y, and then the supremum over x, this inner infimum evaluates to -1 no matter what x is, so this gives you -1, which is not the same as 1. So even though the function here is continuous, differentiable, whatever, bounded from above and from below, all the minima are attained, minima and maxima are attained. So this is not what is gonna. None of these things is helping here. Okay. Okay. So then, if we now have defined what a saddle point problem is, let's define what the corresponding primal and dual problems are. So here we go. That's the next definition. 15.3. For a saddle point, problem, we define the function f of x as the supremum over y of L of x and y, and capital G of y as the infimum over L of x and y over x. And then the primal problem, corresponding to the saddle point problem, is minimize over x f of x, and the dual problem is maximize y over y g of y. And you see that this is exactly, that is totally related to the saddle point problem, because kind of maximizing this g is one of these two conditions here, and minimizing is the other, basically. Okay, so now we fixed the saddle point problem, primal problem, dual problem, although we defined saddle point problem out there already. Okay, and then what is clear? So if x and y star is solves the saddle point, and this implies that x star solves primal and y star solves the dual. And you also moreover have f of x star equals to g of y star. So the primal and the dual optimal values oops, I'm off screen here. So once again, if x star and y star they solve the primal, solve the saddle point problem, then this implies that x star is a solution of the primal, y star is a solution of the dual, and the primal and the dual optimal values coincide. Okay, a little bit more terminology before we come to the break. Yeah, so terminology. So if we really have that inf sub equals sub inf, so if inf x sub y of L of x and y equals sub y inf x of L x and y, we say strong duality holds. So if there is no strict inequality, there's no inequality but equality in the min-max inequality, then we say that strict inequality holds. And if we have this, if we have that this is larger here, then we speak of weak duality. Which always holds. So this is kind of not really necessary, but this if we have strong, something has to be weak. So in terms of the primal and the dual problem corresponding, it always holds that the infimum of f of x is always larger or equal to the supremum of g of y over y. This is then weak duality, and strong duality says that both values are equal. Okay. Note that this is again weak duality, and if you have equality, then you speak of strong duality. Note that even if you have strong, so if you have equality here, you speak of strong duality. But note that even if you have strong duality, it does not imply that either of these suprema or infima is actually attained. They both can be just may not be attained. Okay, and then the difference between the two is often called duality gap. So the difference in both cases, either here or there, it's called the duality gap. And so if you don't have a duality gap, then you have strong duality. That's how the terminology goes. Okay, that was that. That was probably the first half. In the second half, now we're going to state a nice theorem which says that under familiar assumptions, you have strong duality, and you even have that at least one of the two problems has a solution. Okay, but before we come to that, we will have a short break with a few dad jokes. So see you then. Okay, so welcome back to the second half. Okay, now we're going to specialize our notion for saddle points, primal and dual problems to the problem which we started with. So, and recall that the problem was to minimize f of x plus g of ax. So this is now our primal, and it makes sense to call it primal problem because there's the corresponding saddle point function L of x and y is f of x plus ax times y minus g star of y. This is now the saddle point function, or the saddle function. And then we have the dual, which is then maximize over y minus f star of minus a transpose y minus g star of y. This is then the dual. Primal problem, saddle point function with the corresponding saddle point problem, and the dual. This is not only called saddle function, it's something also called Lagrangian, because it's actually related to the theory of Lagrange multipliers. I think you can see that if G is, for example, in the case of linear constraints, then this Y actually is are Lagrange multipliers. But even in this context, they are also called Lagrange multipliers often, even though this is not a constraint here. Okay, so this is then the primal objective. So this is also what is our f of x, and this is the primal objective. This is our g of y. This is the dual objective, and the duality gap is of course f of x minus g of y. Okay, and so now we have a proposition, and this is actually the first thing where we see that it's really helpful to know the dual problem, because if you have some pair of if you have some x, you can always calculate a nice upper bound to the distance to optimality if you know the dual problem, and this works like that. So if you have f and g proper, convex, and lower semi-continuous, and a of the corresponding size, then the gap function of some x and y is primal value minus dual value, which is f of x plus g of ax, minus this, so this all turns into pluses here, it's plus f star minus a transpose y plus g star of y, which is nothing else but this capital F of x minus capital G of y. Then this, I forgot to say that, this is always non-negative. And moreover, for any pair x bar and y bar not being optimal, but we need that g of y star is larger than minus infinity, you have that the gap of x and y is actually an upper bound for the distance to primal optimality. And of course, you know, this is always positive because this is the smallest you can get. You subtract more than you have, less than you have. So this is the gap function. It's always non-negative, but it's also an upper bound for the distance to primal optimality. And the proof is again very simple. It's really all the magic happened before. You know that f of x, should I use a bar? Yeah, f of x bar is larger equal to infimum over f of x, which is by weak duality. So this is why one uses this word here, larger than the supremum over g of y over x, which is in turn larger than g of y bar. So this also shows you this inequality here, so you subtract less than you have, so this shows that the gap is always non-negative. But also you can deduce that f of x bar minus the infimum over x of f of x is smaller or equal to, so you subtract less, so you get more f of x bar minus g of y bar, and which is exactly the gap of x bar and y bar. That's already it. And so it sounds natural that there should be a corresponding statement for distance to dual optimality, and there is, and you may just derive that for yourself. Okay, so that's very nice. And this says, so if you want to solve the primal problem, you don't know how good you've done up to now, so you produce some x bar and think, well, how far am I off from the minimal value? The only thing which you need to produce is one dual variable y bar, which produces a finite value for the dual objective. And once you have that, you can just calculate f of x bar minus g of x bar, and this is an upper bound for the distance to the optimality to the in terms of the objective value, objective function. But in some sense, in some cases, and in some interesting cases, even this producing a point where the dual objective is actually not minus infinity, it's a challenge. So sometimes this even involves computation. We will see this in the next lecture when we apply Fenchel-Rockafellar duality to recover the duality of linear programs. Then both f and g, or the prime and the dual problem, will be linear programming problems, so linear optimization with linear constraints, and then duality, so producing a feasible point in the dual is sometimes a challenge. But anyway, other problems it's not, and then this gives you a very simple check how good you've done. And if you can find a dual problem, a dual value which gives zero gap, then you're optimal, right? This is also something. The gap is zero if and only if x and y are optimal. Okay, so now we are almost done with the lecture already. The last thing we're going to do for today is to show a condition under which we have strong duality, and more, that the dual problem has a solution. Okay. And the situation is a little bit like it is for the subgradient sum rule, that there are different conditions which are going to make that happen. Okay. So this is the Fenchel-Rockafellar Duality theorem. So I just write down all the conditions. You need f from Rm to the extended real numbers, and g from Rm to the extended real numbers, proper, convex, and lower semi-continuous, and a corresponding matrix of appropriate size, so m times n. And then the theorem goes like this. So if it holds that, and now comes the condition which we know from the Touche-Précis theorem. If it, you know that the union over all non-negative lambda and lambda times the domain of G plus, minus A times the domain of F. If this is the full Rm, then strong duality holds. And this means that the infimum over f of x plus g of ax over x is equal to, and here we can write maximum over y minus f star minus a transpose y minus g star of y, and especially the maximum is attained. Okay, so this is that's a big deal, because this condition is usually not that hard to check. So you have to figure out the domains, and you have to and map one domain by A. And so what it means is kind of that this difference here, or what you can also check, if this difference here, the domain of G minus A times the domain of F, if this contains a ball around 0, then this union is the full Rm. So if this contains a full dimensional ball, then you're done. And this, for example, does not need that this domain of G contains a full dimensional ball or the domain of F, just kind of the combination has to be enough. Okay, so this is kind of a nicely weak condition. Okay, and the proof is also not that hard. So but one thing one should also stress is that it gives you that the dual problem has a solution. So sometimes if you can apply Fenchel-Rockafellar to the dual problem again, you will get the existence of primal solutions, which we don't get under proper convex and lower semi-continuous for both terms. It may still be that the infimum is kind of attained at somewhere at infinity. So, yeah. Okay, so let's prove it. And the proof is it's not hard if you do it right. And of course what you need to do is we need to put this in a situation where we can apply the Touche-Précis theorem. And we recall that the Touche-Précis theorem also tells you that the special infinite convolution is attained, and this conclusion allows that we get that the maximum is attained. So how we do it? We move to the product space and we define a function capital phi, defined on Rn times Rm, which is very simple, just doing f of x minus g of y, which is then proper convex and LSC. And you also define a set M. The set M shall be the pairs x and ax. So this is again in the same base set, Rn times r to the m, and over all x and Rm, which is, by the way, exactly what we're going to call the graph of the map A, or the tuples of point in the domain and point in the image. So this is the graph of A. So our aim is to show that the union over the non-negative lambda times the domain of phi plus m, plus minus m, is the full space Rn times Rn. So first we show that, and then we'll see that this is what you need. So let's show that. So we have this assumption here that this is the full Rn. So let's give this here probably 3 stars for now. So by assumption 3 stars. Sorry, first I need to introduce the variables. So we start with 2 variables. Let x and y be in Rn times Rn, and we aim to show that we can write this x times y in this way. So lambda times something in the domain minus something in the graph of A. So and done by assumption 3 stars. There exists a positive or non-negative lambda, a u in the domain of G, and a v, a v in the domain of, so it's u shall be in the domain of F, and the v in the domain of G, such that we can write this y minus tx. This is then some point in Rm. So, but any point in Rm can be written like that. So it can be written like lambda times v minus tu. So we basically just used that here and applied it not to y but to y minus tx. And then I forgot one thing. So so similar to the proof of the Artus-Bresis theorem, which was 14.5, lambda positive works. So we remember that we kind of removed that we needed the so if we have this with lambda non-negative, you also have this with lambda positive actually. Okay, and if we have lambda positive, we can define an A as u minus x divided by lambda. So why we do that? Because then if A is u minus x over lambda, here we have that one thing is that x is lambda times u minus a, and y is lambda times v minus ta. Yeah, so what you do is you bring the tx over here and induce that you have that, and then you see that you arrive over there. Okay. Okay, but from this you know that the pair x and y is so x is of the form lambda u minus a and y is of the form lambda v minus ta, and this is exactly that this is in the form of this is in the domain of phi minus m, because so what lambda negative, because you have here in the first component you have of course lambda times, and then you have this u minus v, and u comes from the domain of f, v comes from the domain of g, and that's exactly the domain of phi. So this times that is the domain of the capital phi, and here you subtract a and ta, and a and ta, these pairs are exactly the ones who come from m. So this representation here says that you have this inclusion here. So this aim here is now proven. So why does that help? Okay, now we apply the Artus-Bresis theorem 14.5 to phi plus psi, and with phi, as you already have, f of x minus g of y, but for phi we use phi of x and y is the indicator function of the graph of x of a. Okay, so because we just proved that q, what the condition we needed for our touche précise to hold, is fulfilled. For phi and psi, because, well, the domain of psi is exactly the set M, right? This because it's the indicator. So hence theorem 14.5 shows us that the conjugate of phi plus psi is equal to the infinite convolution of phi star and psi star, and the inf convolution is exact. So, and this is much more than we need actually. So to complete the proof we just need to use this equality here at the point 0, because we've seen in the beginning that the 0 and the dual kind of characterize the solution in the primal. So at 0 this reads at, so phi plus psi conjugate at 0 is then, let's write this down, is a supremum over x and y over minus phi of x and y minus psi of x and y, because so we have 0 here, so there would be an inner product with in front, but this inner product is with 0, so it doesn't do anything. So, but what is this? It's the supremum over, and let's plug everything in. So phi is f of x minus g of y, f of x minus g of y, and psi is the indicator of m, and m is the graph of a, which means that for this to be finite we have to have that y is equal to ax. So this comes from, this is the definition of phi, and this is the definition of psi. And then we see that this is exactly the supremum over all y. No, that's no, not y. We're going to throw y out because y is always ax. It's the supremum over x. There's a minus missing here. Minus f of x minus g of ax, because we know that y is always x of a of x. And this is then exactly the minus the infimum of f of x plus g of ax over x. So that's the left hand side here. So the left hand side actually exactly evaluates to minus the primal objective value. Okay, and what is the right hand side? The right hand side is phi star infinite convolution with psi star at 0. This is then taking the minimum over all decompositions of 0, which is the minimum over x and y, and here you have phi star of x and y plus psi star, and now you need something here you put something here which adds up with this to 0, so it has to be minus x and minus y. Yeah, and if we check what this means here, so a little bit of calculation, which is basically not hard to do. So phi star is the indicator of the graph of the transpose or the adjoint operator of minus the adjoint operator. So this evolves to minus the minimum over x equals minus a transpose y, which comes from calculating the conjugate of the indicator of the graph of a linear function. And so this here conjugating phi is simple because it's kind of separable. It's f of x plus g of y. This is then exactly f star of x plus g star of y. And the most important thing is you have the minimum attained here by exactness, right? This is exactness, which shows you that you can put the minimum over here. And so it remains to eliminate the x, because you know the x is always minus a transpose y. So this is the minimum over y f star of minus a transpose y plus g star of y. And you know that these two things are equal, so having these two things equal multiplied by -1 shows you exactly what we wanted to have. So the primal problem equals the dual problem, and the multiplying by -1, putting the minus in here, turns them into a max as claimed. Okay, so the only thing which we could check is that this adjoint here is actually or this not adjoint, but this conjugate phi star is actually the indicator of the graph of minus a transpose. So this is well, it's a simple calculation to see that. Okay, so that's Fenchel-Rockafellar duality. It was quicker than I thought. But anyway, let's go through the lecture once again. What have we learned today? So what have we learned? Maybe I could move a little bit closer here. Oops. So what have we learned? So that was our motivation. You probably don't need that. So first we learned the notion of a saddle point problem. So a saddle point problem is you have a saddle function defined on the product of two spaces, and you want to find a point which either gives you the smallest value, or like here or like that, or if you plug in the second one, then the first one is the minimum, and you plug in the first one, the second one is the maximum. And this is exactly characterizing what saddle points in the obvious sense are. So a point where you can only go down in one direction, only go up in the other direction, in the two coordinate directions. So if it goes up here and down there, that's a saddle point. So kind of your legs hang down the directions where the y is moving. And okay, so we learned the min-max inequality, that if so what you do first matters more. So if you first infimize, you get the smaller value, or a value which is smaller than the one which you get when you first supremize. So what you first do matters more. That's the min-max inequality. And then you can characterize saddle points by the property that you can swap in the min-max, because this always holds, and if this shows it holds in the other direction, and this shows all the chains of inequalities. Okay, most notably, and this is important to remember, this can always be strict. This is not really something against that. It may always be strict. So even in all cases, if it's non-strict in a problem class, that's always a mentionable result. Okay, and then we learned the notion of primal and dual problems. For each saddle point problem, if you only supremize over the second or infimize over the first, you get two new problems, minimization and maximization problems, and these are the so-called primal and dual problems. So in primal, basically because x comes first. So we learned about the notions of strong and weak duality. Weak duality always holds because of the min-max inequality, and strong duality is always a result. Okay. In the context of our special case, we see that we have this specific point of primal, dual, and saddle point function. Saddle point function is the one where everything is decoupled, the convex part in x plus the linear part in x, which is also linear in y, minus the convex part in y. Okay, and so then supremizing and infimizing gives you the primal and the dual problem, which are both of the same type, basically. It's a convex minimization problem of f of x plus g of operator x, and the other is a concave maximization problem of f of minus operator y minus f star minus g star of y. Okay, one important so practical tool is the so-called duality gap. which is primal value minus dual value, and this always gives you an upper bound for the distance to optimality. So you can always squeeze the distance to optimality between 0 and anything which you get if you plug in anything in the dual, which gives you something which is not minus infinity, which may be a challenge. We come to that next lecture. And finally, we get the Fenchel-Rockafellar Duality theorem, which says that under some regularity assumption here, that the primal and the dual are the same, so you have strong duality, and the dual has a solution. Nothing is said about the primal having a solution. For this, you would need something more, something like, for example, coercivity or something. These conditions may be hard to decode in the first, so in the beginning, but it gets easier. So, for example, what you can see is if this contains an open ball about some point x at which at some point such that at some point which is of the form a of x for x in the domain. So if you have y being in the interior of the domain of G, but also being of the form a of x and x in the domain of f, then this here contains a ball around 0, and then you get that this union is the full space. So this is one way to decode this. But there are other possibilities, right? Only this difference needs to contain a ball. So it may be that this is kind of large stretch in one dimension, and this has stretch in all the other dimensions, so that the difference is large enough. But it has to contain 0 for some value. Okay. This is Fenchel-Rockafellar, and it's not so hard to check in many practical applications. You're probably going to do that maybe in the exercise classes or here in the lecture. So next lecture will be applications of duality, and so we deal with optimality systems. And then we have this short kind of detour in the lecture where we have 6 lectures about optimization algorithms for convex optimization. So optimal algorithms for optimization. This will be 6 lectures starting from next week. Okay, that's it for today. Thanks for listening, and see you tomorrow.